Now, what about the other end? That's the Big Bang. Now, how do I get away with that? Well, I have to remind myself what the next picture is. Yes, the next picture has to do with that. This has to do with the second law of thermodynamics. Now, this is a very important feature of this scheme, and let me say something about that. I told you that you could have this great mess as the beginning, in which case this wouldn't work. The great mess, if the universe had been started off with that great mess, which apparently didn't start off like, then this trick would not work. But if the universe started off nice and smoothly, then maybe this trick does work. And I want to say something about that. And this comes down to the second law of thermodynamics. Now, what is the second law of thermodynamics? It's a thing which says that entropy increases with time. Now, what's entropy? I'm not going to give you a definition of what entropy is, but roughly speaking, it's a measure of randomness. So it's telling you that randomness increases with time. Now, it always puzzled me a bit here, because another way of saying the second law of thermodynamics is that if you decrease time, then randomness decreases. So as you go back in time, things get less and less random, more and more organized in a way. So you go back and back and back in time, and what is the earliest thing that we actually have direct evidence of? Well, it's this microwave background. This is this radiation which permeates the whole universe, and I said it won the Nobel Prize twice. The first time was the observation of it at all. The second time was more or less this curve. Now, what is that curve? That curve is, the x-axis represents frequency. I'm talking about light, electromagnetic frequency this way, and the y-axis represents intensity. So this curve is the famous Planck curve, which started off quantum mechanics. This tells you that if you have a system which is random, say a gas and particles and gas and electromagnetic fields running around, then they will reach their maximum entropy state, and the radiation will follow this curve here. So that curve is telling you that this is a maximum entropy state. So what do we find? This is the observation. This was the original COBE satellite, which was sent out to measure the microwave background radiation, and they found that it follows this curve extremely precisely. I've got these error bars. Those are these lines going up like that. They're exaggerated by a factor of 500. So if you really drew the error bars, they would be hugging the curve well within the incline. So it's a very, very precise Planck curve. And this is what we actually see in the microwave background. Now, just bear in mind the things I've been saying here. You go back and back and back in time, so the entropy is coming down and down and down and down. So you're getting something less and less random. The entropy is coming down and down until it reaches what you see in the microwave background, which is this curve, and that represents maximum entropy. Now, you don't have to be a mathematician to realize there's something fishy about that. It's saying that the entropy is coming down and down and down until it reaches a maximum. Minimum? Maximum? You'd have thought it should be a minimum. Now, I find this very puzzling, why cosmologists never worry about this. At least they don't seem to worry about it. I suppose they really do. Why is it that you go down and you go back and back and back in time? You should be reaching a minimum of entropy, and instead what you see is a maximum entropy. Is that not a paradox? Well, it's not a paradox for the very reason that what you're seeing is matter and radiation in equilibrium, basically. The universe is expanding, so you've got to correct for that. But that's not the important point. As Tolman well understood a long time ago, the important point is that you certainly are seeing a maximum entropy state back there. Now, how is it that the entropy could go up from being a maximum? Well, the key point is the following. I hope I've got my slides in the right order. Okay, this is illustrating the second law of thermodynamics. The top three pictures here, time is going up from left to right, and the entropy is increasing from left to right. Here we have a gas in a box, and I imagine that it's sort of trapped up in a little container which you would have to open the door and let it spread out. And as it spreads out through the box, that represents an increase of entropy. And that's perfectly consistent. Now, let's suppose that this box is not a box of gas, but it's a galactic scale box, a huge box containing a lot of stars. And these stars are randomly distributed in the box. Now, what happens if you just leave them? They start to gravitate, they attract each other, and they start to clump. And eventually, they produce a black hole. So now, again, I have, from left to right, entropy increasing, but the picture looks very, very different. The entropy is increasing from left to right, both with the gas in the box and with the gravitational effect now. So there's no gravity in the top picture. There's gravity dominating in the second picture. When gravity dominates, then the increase of entropy is represented by a clumping of material, not a spreading out of material. So what we see in the early universe is a combination of the top right picture and the bottom left picture, those two together. And sure, that's what we see. But when you think of gravity, that's low entropy, not high entropy. So the real puzzle, not a paradox, it's a puzzle. The real puzzle is that whereas everything else seems to be randomized as much as possible, gravity was completely the opposite. It was completely unrandomized. It was a very, very low, unlikely state. So this is the key point which the whole model that I'm going to describe to you depends upon, is that the universe apparently started off in a very peculiar state in which gravity was treated completely differently from the rest of physics. And this point has worried me for a long time, and I had various different ways. Let me first explain just a way of characterizing this. I mean, this isn't telling you anything physical, it's just telling you something mathematical. How would you actually say that the uniform is free of gravitational degrees of freedom? Well, I used to say, well, it's a thing I call the Vial curvature hypothesis. Now, to tell you what that means, I'd have to tell you what Vial curvature is, and I'm not going to. All I'm going to say is that this Vial curvature in this hypothesis is for some reason unknown 0 at the beginning. So that tells you that the gravitational degrees of freedom somehow were initially set to 0. By God or by what? Who knows? By quantum gravity? Well, that worried me a lot, because quantum gravity, whatever it is, should be a theory, quantum, that's symmetrical in time direction, gravity, that's symmetrical time, one way or the other. Why do you get this huge difference between the Big Bang, where the entropy is very, very low, very uniform, and that great mess that I illustrated before, which would be the future evolution with black holes and messing together and all that stuff, which is a completely different picture. So although they're both what we call singularities, where the equations all go wild and things go to infinity and all that sort of thing, it's a completely different kind of infinity. The Big Bang is an infinity where the gravitational degrees of freedom were set to 0, and in the black holes and everything, it's the other way around. And so I puzzled around about that for a long, long time. And I used to think, oh, well, that means quantum gravity is some completely crazy asymmetrical quantum theory. And that's what I believed for many, many years. I have a different picture now. And this different picture is what I'm going to try and describe to you. But let me first explain, how do you characterize the fact that the gravitational degrees of freedom are not excited? And I said it's this Vial curvature hypothesis. Well, one of my former students, Paul Todd, introduced a much nicer way of saying it. And let me try and explain this much nicer way of saying it. So that will be, if I've got my slides the right way around. Oh no, before I've got that, let me explain this, sorry. It's very important that the gravitational degrees of freedom were not set to that they were set to 0. You see, what that means is that material was originally very uniform, and then it started to clump. And the starting to clump is very important to us here on our planet, the Earth. Well, you see, what does the sun do for us? Well, people often say, well, we get energy from the sun. That's not the key point. The key point was made by Schrödinger, and people used to attack him for this. He was completely right. The key point is not that we get energy from the sun. Suppose that the sun was not well, suppose that there was the heat of the sun was uniformly distributed over the whole sky. It would be completely useless. If the whole sky was completely the temperature of the sun, we'd have much more energy coming. Utterly useless. Why is it not useless? Not because the sun is giving us energy. The point is it doesn't give us energy, because we get energy from the sun and it goes out again at night. If it didn't go out, we just get hot. I mean, okay, global warming is making us hot, but that's a much, much smaller effect. If we didn't release that energy back into the sky, we'd be frizzled in a few days. There's no question about that. So what's the important point? The important point is that the energy we get from the sun is from a hot body, and the energy going out in the night is cold. The sky is cold compared with the sun. And according to Max Planck's formula, E equals h nu, you get the hot body will release, these are much more energetic photons, and so far fewer of them, and many, many more going out. So the point is that you get many, many degrees of freedom going out, very few coming in, and the fact is that we get low entropy from the sun. That's the key point. Not the energy, but the energy is in the form of a small number of photons, and it goes out in a large number of photons. That means you have the energy parceled up in a small number of degrees of freedom, and that's what plants use to grow, and we live by living off plants, or animals which live off plants, and so on. So the key point I want to make is that the low entropy is what we live off. And the low entropy is because we have a hot spot in the sky, which is the sun. Okay, that hot spot comes from all sorts of things, nuclear physics and so on. But the key point is that the sun's there at all. If there were no nuclear physics, you'd still have a hot spot in the sky, which would be just gravity. So the point is that we have a hot spot in the sky. And why do we have a hot spot in the sky? Because of the material which clumped gravitationally to make the sun. So that is we live off the fact that the universe was previously uniform, and as it clumps to make these hot stars, that's where the entropy is converted into a useful form, and that's what we live off. So that's the point I wanted to make here in that picture. Don't worry about it too much, because it's not central to the rest of the argument. It's central to absolutely our existence, but not to the argument what I want to make here. Okay. Now here I've incorporated Paul Todd's way of representing the Vowel curvature hypothesis. What is it? Well, I've said before, I've been able to squash down infinity into that finite future boundary, that top line that we got at the top there. Whoops, no, sorry, I jumped ahead too far here. I'm not very good at making this thing work. Here we go. Here is the top part. And now, according to Paul Todd's characterization of what I call the Vowel curvature hypothesis, the way in which the universe was special, it was special in such a way that you can stretch it out conformally. It's the opposite to the Escher trick, where you squashed it down. Now you're stretching it out. And the thing is, we now have a nice way of representing future infinity and a nice way of representing the Big Bang. And the thing is that they're very similar. I remember thinking about this at one point. They seem awfully like each other. I might say they're awfully different, aren't they? The remote future, very rarefied, low density, very, 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 very cold. And the Big Bang, very, very hot, very dense. How could they be the same? Now, the thing is that if you have this conformal squashing, that it also makes things get hotter. And so that the Big Bang, the hot Big Bang, is really conformally very much, if you stretch it out, it'll get colder again. So they're very similar to each other. So this was the thought I had, and I was really thinking, let me just see what my next picture is, because I should have remembered that. Well, you see, I should explain that the picture I've just here, there's nothing unconventional about that picture. It's not necessarily the way that cosmologists think about it. They tend not to think this way. They should, but they don't necessarily think this way. There's nothing unconventional about this picture. Well, there is something unconventional about it. That is, I haven't put inflation in the picture. I'll say something about inflation in a minute. But there's nothing really unconventional about that picture. What is unconventional is that. What I'm saying is that our remote future, this is the top part there, squashed down and now this is the Big Bang stretched out. I'm saying they're awfully like each other. So what I'm saying is our stretched Big Bang is the continuation of the remote future of a previous eon, I'm calling it. Our eon is this one. That's the whole universe which I had before. And I'm saying that our Big Bang stretched out is completely equivalent to the remote future of a previous eon. And there will be one after ours. This is what made me think of it first. I was sitting around worrying about the universe, do that sometimes. And I was thinking how boring it is. Okay, it's quite exciting now. All sorts of things happening. You may like them or not, but they're certainly exciting. And but in the very remote future, what will happen? Well, you just get these things are spread out, and it gets black holes. Well, I'll say about the black holes evaporating in a minute, but that's pretty boring. So I thought, well, it's not boring to photons, because photons don't experience the passage of time. That's just the sort of thing I was saying, that if you were a photon, then from the beginning when you were created to when you were absorbed or whatever it is, to that photon, it's zero time. And that's the way relativity works. You see, the closer to the light cone in my previous picture, if I'm prepared to go back further, I'm not sure if that's a good idea, but let's do it. In the picture here, you see, at the bottom, we have a photon zipping along the light cone. It doesn't even hit the first of these bowl-shaped surfaces. So there is no time experienced that photon at all. It's zero. So if you want to have a universe which is boring, well, the photons don't get bored because they don't experience time. They just hit the next eon, you see. And so I thought that's a much nicer picture. It's nicer in another way because I don't need inflation. You see, inflation was supposed to explain something, and the idea is that there is a sort of inflation, but it's not introduced after the Big Bang. It's really this expansion of the previous eon. So the things that it's good for can be still used, even though it's not. You see, cosmologists tend to think of that infinity as squashed into our Big Bang. I'm saying it's not squashed into it. It's before the Big Bang. There was a model like this by a very distinguished Italian physicist, Veneziano. He had a different model, but he did have the same sort of idea that inflation was not after the Big Bang, it was before it. So that is not a completely wild idea, but it's certainly not the conventional one. So I'm saying that you don't have an inflation tucked into the beginning of the universe. It's the remote future of the previous eon. So that is the model which I'm trying to promote. And for many years, I gave talks about this, thinking, well, that's fine. I can talk about this. Nobody will be able to disprove it, so I can go on talking forever about cosmology in this way. But then I had an idea about it, which I shall try and describe. But before describing that, I need to say something about black holes. Here is a black hole, the space-time picture of a black hole. And it's much better to have a space-time picture than a spatial one because you can really see what's going on. The key point is what happens to the light cones. You see the light cones get tipped over in this way. This sort of cylinder up there is the horizon, and that is, once you fall through that, it's bad news because the light cones are tipping over and you can't escape from it without exceeding the speed of light. So you can understand how these black hole horizons work by looking at this these light cone picture. I should say it was Oppenheimer and Snyder who originally had a picture like this in 1939, which is basically what the black hole picture is based on. In the middle, we have this awful singularity where curvatures go to infinity, and it's a great mess. That's the sort of mess I was talking about before. And also you can show that that's a general phenomenon. It's not just a feature of the symmetry that's illustrated in this picture. Okay, so there we have this collapse to a black hole. Now, what happens to black holes eventually? Well, you see, according to Stephen, first of all, this is the picture now with the black holes put in. The red lines are supposed to represent the black hole singularities. So we don't just have this infinite curvature, infinite density, all that horrible problem about the black singularity at the beginning, but now we have this problem also in the singularities in the black holes. Now, what happens to them? Now, this is where Stephen Hawking comes in, and he says, well, black holes are not completely and utterly black. They're pretty black, but they're not completely utterly black. So they do actually radiate. They radiate, this is the Hawking radiation coming out. It doesn't come from inside the hole, it's sort of created outside the hole. And it's a very important piece of work, but Stephen was very disappointed that there was no evidence for these things. And, but it's no good. You see, if you have a, how long is it going to take? See, if you have a supermassive black hole here, the bigger the black hole, the longer it takes. And for the time scale I'm considering here is for a fairly big supermassive black hole. I should explain our galaxy has a black hole in its center which is about 4 million times the mass of the sun. And there are a lot of other much bigger ones. The Andromeda galaxy has one which is 40 times bigger, I think. And anyway, what happens to the supermassive black hole? Well, after a long, long time, and it may take something like a googol years. What's a googol years? That's 10 to the 100 years. So I think of 1 followed by 100 zeros, that number of years. Actually, there are bigger black holes seen now, which the time scale for its decay will be longer than that. An awful long time before that black hole will finally disappear with a pop. You see, it radiates, and as the radiation comes away, it carries energy away, therefore it carries mass away by Einstein's E equals mc squared, and therefore the black hole shrinks and gets smaller and smaller and disappears with, well, I'm calling it a pop because it might be a nuclear explosion or something, it depends on how you measure it, but it's pretty small compared with the mass of the black hole as a whole. Most of it goes out in this radiation. Okay, that's important for us, what I want to say later on. But anyway, these black holes will finally disappear. And there they go, pop. So this, I should say, is not to scale. My previous pictures were fairly to scale. Now they're not. You have to think of 10 to the 100 years, which would be way up the picture. But they will eventually disappear. And then they've gone then. You see, if I didn't have them disappearing, you might worry about joining the eon into the next one. But since they're all gone, you can have a nice smooth final state which joins smoothly onto the next one. I was going to say, why can I get away with the Big Bang being treated as though there was no mass? Well, it's a completely opposite story, but with the same conclusion, more or less. What happens as you go deeper and deeper into the Big Bang? Temperatures go up and up and up and up. That means that particles zip around faster and faster and faster. That means more and more of their energy is in their motion and less in their mass. Ultimately, as you go back into the Big Bang, the mass becomes completely irrelevant, and therefore, again, the universe is dominated by things with no mass. So at both ends, you have the situation, the universe being dominated by things with no mass, and therefore you can think of the conformal picture where the light cones dominate the structure and not the scale given by the clocks. So this is the idea, and therefore physically that my picture makes sense, not just that you can draw them, that it really makes physical sense as well. So that was a key point to what I wanted to say. Okay, well, as I said, I used to give talks without worrying about observation. Then I began to think, well, what happens when these black holes run into each other? I should explain what I told you about our galaxy, that's the Milky Way galaxy, has in its center, Cygnus, a point. It's now you can see the stars going around it, and it's very, very clear. You've got this object, and now people have this picture of a black hole, not our one, but another one, and you can see that there really does seem to be this black hole in the center of galaxies. Pretty well all galaxies. There may be a few where the black hole has got shut out for one reason or another, but on the whole, it seems to be that pretty well all galaxies have. Now, what's going to happen to us eventually? I'm not talking about now, I'm talking about in a few thousand million years. Well, we will collide with the Andromeda galaxy. We are heading for each other. And, well, okay, it might be fun to watch if we were around then, but we won't be. But nevertheless, the black holes will not immediately run into each other, but they'll feel each other out. Maybe the galaxies will go through each other a few times like that before they settle down. And the black holes will feel each other out, spiral into each other, and there will be one whopping explosion, where a considerable proportion of the mass energy of that of those two black holes will be radiated out in the form of gravitational waves. A huge explosion. Well, you probably wouldn't even feel it because the gravitational waves are not things that you feel easily. You need a very sensitive detector to feel the gravitational waves. But nevertheless, they're there, and these black hole encounters, not this kind of scale, but smaller black holes running into each other, are seen by LIGO. And so they're certainly there, and they're doing what people seem to think they should do. So you will get these encounters by black holes, and maybe the gravitational radiation from them can be seen in the next eon. So in this picture, the sort of plane going between them, now that is meant to be a three-dimensional space, which is the crossover between one eon and the next. So below that plane is the previous eon, above it is us, and we are sitting at the top of that cone looking back. This is the light coming, or I should say the microwave background coming to us from the black hole encounter, and we ought to see these gravitational wave signals in the form, you wouldn't see them as gravitational waves, you'd see them, I won't go into the details, but you'd see them as a slight warming or cooling of the microwave background. And these will be circular features, so I've tried to indicate here that they're faint, and I've drawn them deliberately rather faint. And also for a cluster of galaxies, there will be many times that these black holes run into each other, swallow each other up, but if there are lots of galaxies in the cluster, we don't have too many in our cluster, it's only about 4 or something. But there are lots much bigger ones which have thousands and so on of galaxies in them, so that when the black holes run into each other, they're bang, bang, bang like this. And we would maybe, if we're lucky, see them as these rings in the microwave background. And I should say they would either be slightly warmer or slightly cooler. When I say either, it depends on the distance from us. If they're close to us, they will be cooler, and far away, slightly warmer, the way it works. Don't worry about the details. But you would see them as concentric rings, because the galactic cluster would look like one point to us, and the rings would be the signals coming out of that point. Okay, now let me just show you some pictures now. These are pictures produced by my Armenian colleague Vahe Gurzidyan, and he was looking for rings of, well, he had a clever way of doing it. He looked at the variance of the temperature around the ring, not whether it was warmer or cooler, but with the variation in temperature. I won't go into the details of that, but he had a way of looking at it which didn't depend on whether they were warmer or cooler. And if you saw at least 3 with the same center, then he would plot it in the picture. So this was a picture that he produced from the original, this was the WMAP satellite. There were 2, I mentioned the original COBE satellite, then there were 2 others. One was the WMAP satellite, and this is pictures produced from the WMAP satellite. And you see these rings, and there are lots of them, remarkably many. And one reason you can see this as a real effect is that if you look for ellipses using the same algorithm, you can do that. You see that the more elliptical they get, the fewer you see of these rings. So it does seem to be something which depends on them being circular. And moreover, you can see how clumpy the distribution is. Let me give you the next picture, which is the Planck satellite. That's a more recent, more detailed satellite. And you might think maybe they go away with the more detailed information. No, the signal gets stronger. And the clumping is even more clearly evident when you just plot where the centers of these circles are. Another point which is rather noticeable is the color now. You see, he didn't look for the actual temperature of the rings. He looked for the average of the temperature around the ring, and he looked for the, I should say, the variation of the temperature around the ring, and not for the average temperature. But if you look for the average temperature, then the red ones are where the temperature is warmer, and the blue ones are where the temperature is lower. You see, they're not just clumped in where they are, but they're clumped in the temperature. And the temperature is an indication of the distance. So the red lot down here that means more distant according to theory, and the blue ones are relatively closer according to theory. And you see they're clumped not just in spatial orientation, but in the color. So the color means in distance. So that means they're clumped in space. So I don't know of any theory that explain that, certainly not inflation, because inflation would give you a very uniform distribution. So I think people just didn't believe these things because it contradicts inflation. Okay, now this is something else. These are the Hawking points. Now what do I mean by Hawking point? It actually came about because there's a Polish group also looked for the circles, so I should. My picture here was the one that Vahe, my Armenian colleague, that's his analysis. But a Polish group headed by Krzysztof Meissner in Warsaw looked in a completely different way, and they also found indication of these rings. And they assigned, I think, first for the WMAP data, a likelihood of 99.7% confidence level that it was a real effect. Then they looked in the Planck data, and with a likelihood of 99.4% confidence. They submitted their paper to the Royal Astronomical, monthly notices of the Royal Astronomical Society, and they had many complaints from referees, and every time they did everything the referees wanted them to do, and finally they got a note from the editor saying, "I'm terribly sorry, but we're going to have to accept your paper." And the thing was, they couldn't think of any other reason for complaining about it. And the thing is, it goes against inflation, and these things are incompatible with inflation. I won't go into the details why, but it certainly, inflation would not work inconsistent with it. But you could have an inflation in the previous eon, that's perfectly consistent with it. And this is the very non-uniform distribution, which is telling you that there is something very irregular about whatever is producing these signals. And it's easy enough to have a model. I mean, inflation has a lot of trouble, because how do you get this irregularity in distribution? Very hard to see. Okay, now the Hawking points. You see, I had this discussion with Christoph about how to make a little more precise measurements. And so they were starting to look with this more precise way of doing it. And they found, somewhat unexpectedly, for tiny little circles, a very strong effect. And I thought, what are you doing? I thought, maybe you're seeing Hawking points. Now, what's a Hawking point? You see, here we are in this picture. The red plane represents the crossover from one eon to the next. The blue plane just above it represents what you actually see. Now, I should explain that in the conventional cosmology, the Big Bang happened, say, time 0, then time, which is 380,000 years after the Big Bang, that is what you actually see in the microwave background. So the microwave background is not looking at the Big Bang. Sometimes people call it the flash of the Big Bang. It's hardly the flash, because it's 380,000 years after the Big Bang. And it's cooled down from whatever the temperature you expect in the Big Bang to be this microwave temperature that you're looking at. And between the Big Bang and that, you see, I'm trying to illustrate here. Here is a cluster of galaxies, another cluster of galaxies, swallowed by the supermassive black hole. That line represents the history of the supermassive black hole. Then finally it evaporates by Hawking evaporation. Well, I mentioned 10 to the 100 years or longer than that. How does that in the picture? Remember the Escher picture, which all the fish or the dangers and devils squashed up at the end. A period of time like 10 to the 100 years is as nothing in the picture. It's completely squashed up into that little point. And that's just think back to the Escher picture. Very, very long time. If you get right close to the edge, that can be as nothing in the picture. So you have to imagine that it's more or less just underneath this infinity. So you have a huge explosion. Now you see, the Hawking radiation is extremely cold. It's ridiculously cold, coming from the black hole. integrated over the whole history of that black hole. Almost the entire mass of that black hole is contained in that radiation. So you have to think of that radiation squashed into that one point. The entire mass energy of that black hole, which will probably be pretty well the entire cluster of galaxies. So most of that galactic cluster will be swallowed by that one supermassive black hole. That comes out in the Hawking evaporation. So think of that huge, much, much bigger than our galactic cluster, maybe one with thousands or even more of galaxies, all squashed into that one point, that much energy, mass energy, coming through, bursting through into the next eon. What would you see? Well, let me just see if I've got the picture. I think it is in the next one. Okay, you see, this is another space-time picture. The lower line is the crossover from previous eon to ours, and here is your supermassive black hole, all the irradiation squashed into that point and bursting through into that one point. It spreads out with the speed of light, the boundary of it with the speed of light. That's what this cone is doing, or that two lines out there which represent the cone from this point, to what we actually see. That's the microwave background. And that spreads out to how far? Well, that's about 4 degrees in the sky. How big is 4 degrees? That's about 8 times the diameter of the full moon. So the full moon is about half a degree. So think of about 8 times the full moon. That is the spread. And so what I'm saying is that the energy in the Hawking point is spread out, more energetic in the middle, and spread out towards the edge. And as we look back, that's meant to be us looking back, we won't see quite in the middle, but you'll see a good fraction of it. You'll see a intensity in the middle, dying off towards the edge. And what my colleagues did was to look for signals like this. And I should explain that in order to do the analysis, this is you see, my colleague Vowel got into trouble with colleagues because he had an individual doing the analysis. And the proper way of doing it according to standard cosmology is you look for this thing called the power spectrum. Again, I won't explain what that is, but you imagine, if you like, the universe was like a balloon, and you have the different ways it could oscillate. And as you go horizontally, this is the main mode of oscillation, and the different details in which can go is never mind about all that, but the curve represents the intensity for each of these modes of oscillation. And you see it fits extremely well. The error bars, if you look more to the right, fit that curve very beautifully. And what that's telling you is that the physics between Big Bang and I should be getting from Big Bang to last scattering, from here to here, is extremely well known. So it's very well understood. And that is the fit that you see for the curve there. People often say it's a beautiful confirmation of inflation. It's not. It's a beautiful confirmation of the physics between Big Bang and last scattering. So yes. But now I should explain what the pictures are here. Perhaps I should explain by going to the next picture better. What my colleagues did were to look for 2 rings. So you're looking at a ring like this between the outer ring and the little inner ring. And they were looking at the temperature variation from inside to outside. So is it hotter in the middle than outside? And if so, how much? So that's the sort of they're looking for. And for these particular sizes, so I should say this is about 4 degrees across, 8 times the diameter of the moon. That is what I was showing you before. You see a very strong signal. Now I'm only trying to indicate how, oh dear, I've seen 2 of them. No, I'm not doing. I'm jumping around. Why is it going back to the beginning? Oh dear. No, it's gone wrong again. Never mind. The curve I just go with all those points on it. It's supposed to agree with that, but you've got a lot of variation you can do, and you can produce many, many, many maps, thousands and thousands of maps, which agree with that curve. And what you're supposed to do is see how many of the artificial maps show you the same effect. And the numbers that I showed you in the graph here are numbers, you see them in the, well, there were two. First of all, Daniel And, who did the analysis, was looking at 1,000 of these artificial maps. And you see the greens ringed 0 and 1. No, I think they're both zeros. For 1,000 maps, you see not a single one of them shows the effect that you see in the real map. And then, just to make the point, for a particular reason, he did another 9,000, so it was 10,000 altogether. And in 10,000 maps, you only saw 1 or 2, those are the 2 blue-ringed ones there, which see the effect. So this is telling you that the effect is there with a confidence level of 99.98% confidence. So it's even much stronger signal than we had before, that these signals are there in the real sky. Moreover, I should say, according to one complaint somebody made, that if you look, this was done from the Planck data. If you look back at the older WMAP data, you see the same points. And for the 5 strongest points, you see them in exactly the same places. So that these points, let's just take those 5 strongest points, the others might be, say, artifacts, but those strongest points are definitely there, and I claim that you could see them. If you had microwave eyes, you would see there's a sort of variation intensity, which is about 1 part in 10 to the 5, but this is about 15 times stronger. So this variation in the Hawking points is about 15 times stronger than the normal variation in temperature. So I think you would see a sort of glow, a spot like that, at least in these 5 places, which are there. And they seem to be there both in these 2 completely different satellites, examining the sky in completely different ways. I think he did 3 or 4 different ways of doing the analysis, and he saw the effect in all of them. So it does seem that these Hawking points, as I'm calling them, are there. Maybe there is some other explanation for them. It's very hard to see how inflation would do that, because this enormous expansion which is supposed to take place in the inflationary phase would simply wipe out signals of that nature. So I wait to see if there is an explanation in terms of ordinary cosmology, but it certainly is explained on the basis of conformal cyclic cosmology. So I wait to see whether another explanation can be found for them. But anyway, whatever they are, and I'm calling them Hawking points in honor of Stephen Hawking, because of the Hawking radiation would be the dominant contribution to the energy of these signals. Thank you very much.